era of space exploration is here.
The first worldwide incubation program, entirely dedicated to space resources.
Who's the customer? What is the business plan?
Access to its facilities, offer technical support directly from European space agencies, be part of this vibrant ecosystem in an international network of partners.
I think that's where the SSP comes in.
Of space resources
starts now.
Find out how you can be part of the story.
Good afternoon, ladies and gentlemen. Welcome to the Plenary event. I'm Jun Shimura from JAXA. I'm going to take you to the world of space resource utilization. It's about creating valuable products such as oxygen, water, propellant, and construction materials from local resources on the Moon and Mars. We call it In-Situ resource utilization. ISRU in short. The bottom line is that this technology does not exist on its own. It must be tied to users of final products and services. We need to take a multifaceted approach to commercialize space resource utilization, which is the reason I created this session. Please consider how to use your expertise in the realm of space resource utilization. With that, let's invite speakers. Ladies and gentlemen, please welcome 4 professionals from around the globe. Please have a seat. Let me introduce speakers. From left to right, Jelly Sanders from NASA, lead for ISRU Capability Leadership Team, and Jeffrey Hoffman from MIT professor and a former NASA astronaut. He's a deputy principal investigator of MOXIE mission on Mars. And Catherine Hadler, director of ESLIC, European Space Resources Innovation Center, and Simone Pirotta from AGI. And me, myself, is technical lead for ISL research at JAXA. It's so fantastic to have you all here in the panel. Thanks for making this happen. Let's get straight into the first question. Jelly, can you tell us what exactly ISRU is?
Oh, well, thank you very much. So, do you want me to stand?
Whichever you want.
Okay. Yeah, I'll stand. I move around too much anyway. And so I'm going to kick off the activity to talk a little bit about ISRU. Let me go back. Okay, well, slightly different. So as June mentioned, ISRU is everything from what we say prospect to product. You have to understand where the resources are. You then, once you know that, you can acquire them. You start to process them in one way or another, and then you deliver a product to a customer. As June mentioned, you need a customer. It doesn't exist on its own. The other interesting thing about ISRU is that it is very multidisciplined. We heard this morning about all different types of industries. So when you talk about ISRU, your robotics, you know, processing, information, common nav, power systems, all have to be part of this. So then the next question comes about, well, why? You know, why would you use space resources? And I'll point to the NASA Moon Mars architecture strategy document in 2 ways. One is they have a very interesting chart as to why do we go into space? And they break it into 3 different areas: science, inspiration, and national posture. And the ones that fit in the middle of that beautiful Venn diagram are the ones that probably are the most important. And so as one of our jobs, we look at that Venn diagram and what does it mean, and you can kind of plot out, you know, if we use space resources, it has a science aspect, it has a aspirational aspect, and it does have a national posture aspect associated with it that are all very important as to why we go into space. On the other hand, you look at the other part of the Moon to Mars objectives, and it lists, well, what are all the objectives that we want to do when we go into space? And I broke those down into the resource aspect. What are the resources? How do we find them? The usage aspect. And then one area that I think is becoming more and more important is the responsible aspect of space. You know, it's not just doing those things, but you have to do it responsibly. And the document does start to show these objectives as how we would do responsible space. So one of the charts, I give many presentations, a strategic overview. We have plans for space resources from a very long-term vision on the top left-hand side, I guess, from the way you're looking at it. We have a time phasing. We're starting at the lunar poles and what resources are there, the highland regolith and the water that exists hopefully in permanently shadowed craters. And we have a yearly process in which we look at what we've been accomplishing, what are our goals and objectives, what are our gaps, are we filling those gaps? And then just recently, we did a huge scale request for information as to here are all the different types of gaps and shortfalls that we have. What does the community think are the most important for NASA to focus on? And so with respect to ISRU, there were several that bubbled up near the top that we now use in our planning. How is ISRU involved in the Artemis program is another thing. So we look at, there are 4 major segments to Artemis. First is just getting humans back to the moon since Apollo. But once we've done that, we want to start thinking about, well, how do we explore the moon, you know, in longer durations and farther distances? That's our foundational exploration phase. We would then hopefully go to our sustained lunar evolution, stay there for longer periods of time, more people going and such. And then there's the humans to Mars. And when you look at ISRU, you start seeing this gradual movement from demonstrating ISRU to using ISRU as we learn more about the resources and we learn more about operating off our planet. You have to think about our experiences at best 3 days on the lunar surface with a rover and spacesuit that had quite a bit of issues if they had tried to stay there longer. So you got to take these kind of baby steps. Another thing is, you know, what's the role of government and NASA? You know, it causes some people concern when you say, I'm from the government, I'm here to help. But there are things that we can actually do. So one of those things is how do you buy down the barriers for commercialization? And then other is, what is your plan to achieve those accomplishments? And in both cases, NASA's goal, especially the Space Technology Mission Directorate, is to really focus on how do we enable industry to be successful, how do we eventually commercialize these operations, but do it in a very responsible manner. And with that, I'll bring my initial segment to a close and hand it off to the next person.
Thanks for your nice introduction, Jelly. Yeah, let's move on to research activities here in Italy. Italian Space Agency, AGI, is now promoting national initiatives for lunar resource utilization. Simone, take us through what's the long-term strategic plan and where you guys stand at this moment.
Yeah, June. Good afternoon, everyone. As you mentioned, we have several initiatives in this field. We recognize the importance of this field and how it is enabling for a long-term, of course, presence, in particular for the crews. More in general, our initiatives could be purely national, could be as a member state of ESA, and also could be part of international cooperation with more partners in bilateral or multilateral partnership. And we are elaborating a plan that can cover all destinations that are of interest for exploration, the main ones, of course, like Moon and Mars, and for small bodies, and they're both robotic and human and crewed in nature. Of course, for the crewed part, the main project I'm really quickly mentioning is the multipurpose habitation module that our national company TESA is developing to contribute in the Artemis surface architecture as a pressurized outpost that will be part of the lunar polar institution and installation there. It recently had a good achievement and mission concept review, so it has been approved as being part of the official architecture. Of course, in order to enable a long-term operation, it can store a set of resources, can generate locally, but must be rely also on local resources on the moon surface. Now, quickly mentioning about the simulation and mission control center we are developing at Altec in Turin, where the module, the crewed module will be tested, but also it will be very useful for robotic testing. Entering into ISRU, Prospect is an ESA project, European Space Agency, but it has a strong Italian heritage. Our Leonardo company is the prime contractor for that, and it implies the extraction in the South Polar area of samples, and the main goal is to identify volatiles, presence of volatiles into the sample. Excavating and accessing a resource can imply change into the nature and in their state. And of course, we want to be sure of the presence of the volatiles there and learn also how to preserve them in case of the excavation. But probably the main ISRU project that we are implementing, named Oracle, will aim to the demonstration in a relevant environment, meaning the moon surface, of a demonstrator of the carbothermal reduction process as a good way to extract oxygen and water from the moon regolith. We are already in a quite good state because the phase A B1 is running, looking for flight opportunity. This is a really important step. This process has several advantages. I will add a few words now. One of them is that agnostic with respect to the regolith composition, mainly, so we could land almost everywhere. And we soon started the industrial phase, having a launch readiness about 2028. Why this process? Carbothermal reduction is one of the main candidates to extract oxygen from the moon regolith, and it basically has a couple of two stages process where the oxygen is then, the regolith is, I can make it a little bit more real because I have, thanks to Polytechnic of Milan, which is currently running phase A1, maybe one for us, you can use several type of regolith, both from islands and from Maria, and the difference in color is important. It clearly identifies the location where it comes from, and it is collected into a main reactor where the temperature is raised up to 1,100 degrees, more or less. One of the advantages of this process is that it would not imply the melting of the regolith, so it will stay in the solid state. This one is not a good example because the result is not an exhaust regolith, still loose. What we expect to have is a still loose regolith like this, exhaust one. And on the other hand, of course, obtaining, first of all, CO, that then will enter into a methanator stage that will allow us to generate water vapor that then will condense, generating water. I will not cheat on you. This is Milan tap water, but and you can say because it's fancy, more fancy than other, but I will also show you how the methanator of the lab that is here in Milan, in Polytechnic in Milan, looks like. It's this type of device where, and this is real water extractor from lunar regolith simulant, so from a lot of it, because usually the yield is quite a good one, but for this you really need more kilos of regolith one. So just to make it more real, we are running currently all the optimization that is needed. Some trade-off on the configuration side and something on operation and interfaces definition, and so we are confident that we can complete our study by 2020 and be ready for a launch 2028.
Thanks, Shimone, for your inputs. I'm really looking forward to hearing the updates on your project led by Italian companies. Can you make a click, please? Click. Let's talk about Mars. In 2021, the experimental device named MOXIE aboard the NASA's Perseverance rover successfully generated oxygen from Martian atmosphere, which, of course, received a lot of publicity. Jeff, please share your stories.
Yeah, so we've been talking about ISRU for decades, but for the first time, MOXIE actually demonstrated it. The whole point, of course, how to keep Mark Watney, or any other astronaut for that matter, alive on Mars, and how to get him home. Of course, keeping alive, you need oxygen, and he used ISRU. He made oxygen and grew potatoes, and then he finally found his way to the rocket and made his way home. But what they didn't show you in the movie was, where did all that propellant come from? You know, we're aerospace engineers. We know what kind of a rocket you need to get 6 people off the surface of Mars. And you're going to need, assuming it's an oxygen methane propellant, you're going to need 40 tons of propellant, and oxygen is 3/4 of the mass. So we're talking about 30 metric tons of oxygen. Staying alive, you breathe a little less than 1 kilogram of oxygen a day. So this is the real challenge if we're going to come back from Mars. And we talk about the gear ratio, because here's the thing. To land 1 ton of anything on the surface of Mars, you've got to put about 15 tons of stuff into Earth orbit, mostly propellant, but rocket bodies, motors, heat shields, parachutes, the whole deal. 450 tons, that's a lot of stuff for getting oxygen on Mars. So wouldn't it make more sense if we could make that oxygen on Mars? And of course, that's what ISRU is all about. Because 450 tons, I mean, we're talking about 3 to 4 launches of a Saturn V SLS class rocket. Now, it may be that SpaceX will figure out less expensive ways to get there, and I think the economics will ultimately be important, probably more so for the moon, because if you can deliver oxygen to the moon cheaper than you can make it there, then you don't need ISRU. But for Mars, there's also operational requirements, because we can only go there every 26 months. So it's really nice to be self-sufficient. And that, of course, is what the ISRU is all about. So how did we do it? Well, this is a model of MOXIE, just to give you a sense of what the scale is. It was a joint project of Jet Propulsion Lab and MIT. JPL made the hardware, turned it over to MIT to operate and do the science. We landed on Mars in February, and on the very first time that we operated, this was 1 day, by the way, after the first helicopter, the Ingenuity flight, which in itself made history. It was a Wright brothers moment of the first flight of a controlled aerodynamic vehicle in the atmosphere of another planet, and the very next day was also historic because it's the first day that we really extracted usable resources from another planet. Now, oxygen, unfortunately, is not as photogenic as a helicopter. You can't see it, I'm sorry. So this is all I can show you, but this was really exciting when we realized that this was a process. The purpose of MOXIE was to take a process for extracting oxygen from the carbon dioxide of the Mars atmosphere, and it had been demonstrated many, many times in Mars-like environments on Earth, but to reach the technology readiness level of 9, which NASA requires for any critical technology, you have to demonstrate it in the real environment. And that's why we went to Mars, and it worked. So basically the way it worked, very briefly, we take the atmosphere of Mars, we run it through a HEPA filter to filter out the dust, we put it through a compressor, and then into a solid oxide electrolysis system, which is really the guts of MOXIE. How does it work? Well, we have 10 different layers, and each layer has both a cathode, an electrolyte, and an anode. And this is a detail of one of those layers. You have to heat the carbon dioxide to 800 Celsius. Takes a lot of energy. Any electrochemical process that we're going to use for ISRU takes a lot of energy. The carbon dioxide runs over a nickel catalyst with a little help from cerium dioxide, partially decomposes into carbon monoxide and an oxygen ion, and the electrochemical, the voltage on the system pulls the oxygen ions through the scandium-doped zirconia electrolyte, which has a crystalline structure that only allows the oxygen ions to move, then into the anode where we basically get 100% pure oxygen. And the purpose was to demonstrate that this process works on all seasons of Mars and during all times of day. And we ran it 16 times and successfully did that. And at the very end, we can make, with 1 amp of current, we get 3 grams per hour of oxygen. Our power supply was limited to 4 amps, so the maximum we could make was 12 grams per hour, and we did that several times. So it was completely successful. After we demonstrated all of the capabilities, we actually, sadly, but I think justifiably, turned it off in September of 23. And just looking ahead, how do you scale this up? It is a scalable system. It's a scalable technology. And the company Oxeon out in Salt Lake City, which made the electrolysis unit for MOXIE, has already demonstrated that they can build a full-scale system. You have to scale it up if you're going to fill up that rocket in the 26 months that you have between flights to Mars, from 6 to 12 grams an hour to several kilograms an hour. And as I said, you need a lot of electrical power. So that amount of oxygen production is going to take on the order of 25 kilowatts. We're probably talking nuclear power. And as I say, any electrochemical process is going to require that. And so that's basically what we did with MOXIE, and it was a great success. We have done ISRU for the first time.
What a great achievement. Well, let me ask you a quick personalized question for you. You flew 5 missions as astronaut into space aboard the space shuttle, including EVA activity to repair Hubble telescope. You must have a profound understanding and instinct for survival. And what do you think the ISRU technology gives any sense of security to the future residents?
Yeah, I mean, if I were going to go to Mars, sure, I would like some oxygen to breathe, but as I said, I don't need a whole lot. I'd be very nice to know that we can make enough oxygen for the rocket that's going to take me home. But the other thing, you know, this is we're talking about an era where we have people who are able to maintain the technology. Once we get to the scale of technology like this, things are going to break, they're going to need to be maintained. Mm-hmm. And so I think, as we demonstrated with Hubble, spacesuited astronauts can do a lot of very useful work and keep these very complex systems operating.
Mm-hmm. I appreciate that. Thank you, Jeff. Well, can you make a click, please? Yeah, now we got a recipe, a piece of recipe, but the question remains, what is the first step to take to commercialize space resource utilization? And what should be done by the public sector to support startup companies to ensure long-term sustainability? Catherine is looking for the answers to those questions through her job at ESLIC. Let's start the video first.
Space resources will be driving the future of space exploration. In today's booming space sector, the space resources community is consolidating. and fosters the development of ideas, concepts, technologies, and business opportunities. The ESRIC Startup Support Program is the world's first accelerator and support scheme dedicated to space resources. It is open to startups worldwide. It provides tailored support to the best ideas with terrestrial or space applications and goes through 3 phases building on each other.
The future of space resources starts now.
Catherine, can you tell us the mission of your institution?
Thanks, John. Thanks very much. So let me give you a short introduction to ESRIC. ESRIC is the European Space Resources Innovation Centre. It is the first, worldwide first innovation centre that is entirely dedicated to space resources. We've heard that ISRU has been around for a number of years. ESRIC is relatively young. It was launched 4 years ago in November 2020. We are an initiative of the Luxembourg Space Agency, Luxembourg Institute of Science and Technology, and we work in strategic partnership with the European Space Agency. We are based in Luxembourg, and we have a very clear mission. Our mission is to be a world-leading centre of excellence in the science, technology, and business of space resources, to support the human and robotic space exploration, and for the future in space economy. The way in which we do this is in 3 separate activities. Firstly, we are a research and innovation centre, so we do research. I have a large and active research team that do research across the lunar resources value chain. We focus specifically on oxygen from regolith at the moment, but not exclusively so. Not only do we do our own research, we are also developing research and development facilities for the community. In our commercialization activities, you've already seen the incubator that we run with ESA. This is the Startup Support Program, but we have a new accelerator program as well that we are currently launching. And in our community activities, we bring the community together in Space Resources Week and with our challenges in partnership with ESA. In terms of our facilities and labs, we have labs in which we do our own research. So we have beneficiation, oxygen extraction, and purification. But we're also building up facilities for the future, for the community. And this includes a large dusty thermal vacuum chamber. This is being built under ESA contract by a consortium, and then will be hosted and operated by us at ESRIC. In the future, this will be joined by a ground-based pilot plant, which will be based again on the lunar oxygen value chain. In terms of research, we've heard already that space resources is a broad, multidisciplinary field, and our research reflects that. We do research from prospecting, understanding resources, through to extracting oxygen and metals, beneficiation, and purification. But in addition, we are also looking at ways in which we can support a sustainable and responsible use of space resources. And this includes concepts such as recycling of end-of-life equipment and minimizing future legacy. We've already heard about the Startup Support Program. Let me give you a little bit more information about this. So this is an incubator program for space resources concepts. It runs twice a year in partnership with ESA. It is open to anyone from around the world with a space resources related concept. From the applications, 5 get supported into a remote 12-week pre-incubation phase. And from those, 1 of those will get supported into a full incubation in Luxembourg. We've run this for a few years now, so you can see on the screen the 3 startups that we have incubated in Luxembourg, and we're currently evaluating for the 4th and 5th cohorts. And finally, Space Resources Week, we run every year in Luxembourg in spring. This year we had 550 people online, which admittedly is a drop in the ocean, a drop in the lunar ice compared to this conference, but actually this is the largest gathering of the space resources community globally. It's a really dynamic and active session. This year we ran in parallel with a UNUSA expert meeting, which made a really fascinating mix of people from science, technology, business, startups, and also from legal and policy backgrounds. Next year, it will be in May, from May 19th to the 21st. Thank you very much.
Thank you, Catherine. Well, one of the most inspiring aspects of your program is its inclusion policy. It's not limited to domestic startup companies. It's open to the application is open to the world. What's the main reason to take that approach?
I think we can all agree that space resources is a global activity. And so we are interested in supporting and attracting the best companies, the best ideas from all over the world, and really bringing into the very dynamic Luxembourg space resources ecosystem.
That makes sense. Thank you. Yeah, given those presentations, let's move on to the discussions. When tapping into local resources in space, resource prospecting comes first. Simone, what is the key element for resource prospecting?
As we mentioned, the prospecting phase is critical and enabling. It's the preliminary one. We need to assess the resource, we need to detect and identify it, and then also characterize, and also quantify, because the quantity can make the difference between a resource and a reserve, and it can make this more attractive, of course, and interesting. So we are in the phase when we are benefiting from scientific missions to have information about the resource presence, but probably now it's time to have dedicated initiatives for, and it's now there are several running about it. So we need to move in situ, not only the mapping from orbit, but moving in situ and start having information about the status, because extracting reserves also deals with their composition, how the chemical species that we're looking for, they are bonding, and which type of energy we need to access the resource.
Okay, I see it. So in a nutshell, the first step to take is to locate candidate lesions and get the ground truth data. That's where we are right now. And given the variety of space resources, what are the highest priorities to ensure long-term human presence on space frontiers? Jelly.
Well, thank you. What I like to say is the most important resources from ISRU are the ones that provide the biggest benefit as early as possible. Jeff mentioned propellants, for example, and the gear ratio. Those are critical that over time, if we're going to go to the moon or Mars repeatedly, having to take lots of propellant with us and minimizing what we can bring is just not sustainable over time. Commodities, whether it's for life support systems and crew, for cleaning, for growing plants and such, those are very important. And if you look at this chart, it kind of shows the balancing act of no matter where we go, water is one of those things that we're always going to want and find. It's so very useful, from radiation shielding to drinking to propellant production. Oxygen, carbon is incredibly important. Sadly, the moon doesn't have a lot of carbon, but if you want to start making plastics, if you want to start making hydrocarbon fuels or nutrients, you'll need carbon. And then metals. Obviously, if we're going to be there for longer periods of time, Jeff mentioned repair. Think about the amount of logistics you need to bring with you to Mars if you want to cover every piece of hardware that might fail. So you're going to have to build an in-situ manufacturing and repair capability. Metals and plastics are going to be incredibly important.
I see it. Thanks, Jelly. Catherine, you started your career as a scientist specialized in mineral processing and beneficiation, which is separating valuable minerals from others, if I understand correctly. And my question is it technically possible to apply existing processing methods on Earth to space resource utilization?
Absolutely. So space resources is fundamentally about resources. And we have a huge amount of experience and expertise on Earth from taking naturally variable, naturally occurring materials from Earth and converting them into something that's usable. So we do have that experience. And if we take terrestrial technologies in, for example, excavation, beneficiation through to extraction, then that's probably a good place to start for our space resources technologies. However, they need to be adapted, and they need to be adapted to operate in the space environment. So under low gravity, under vacuum, with large temperature swings, with no processed fluids. So we can't make use of water and air like we do with many of our process technologies on Earth. And in doing that, we also can rethink a little and adapt the design for the space environment. And this also includes in minimizing waste, which is one thing we have a quite poor track record of Earth. Now, in doing that, in rethinking for the space environment, in adapting, we can learn a lot of lessons of how to transfer those concepts back to terrestrial mining. And I think that's one of the most exciting things about ISRU.
Thank you. Well, let's shift gear to Mars. Let me ask you, Jeff, does humankind have sufficient information regarding Mars resources to start discussions on ISRU at this moment?
Well, you're asking why we went after oxygen first?
Yeah.
Because it's easy. I mean, we know there's a lot of water on Mars. I mean, that's the next thing up here. But the water that we've found so far is all at high latitudes. Even the liquid water that we believe is under the South Pole, and it's really deep. You have to drill for it. You need an industrial operation. Then you have to transport it. I mean, the great thing about getting oxygen out of the atmosphere is everywhere. Doesn't matter where you are. And so that's why we went after the oxygen first.
That makes sense. Thank you. Well, Jelly, I found this illustration on NASA's website. What are they doing on Mars? DIY on Sunday?
So this goes to the next story about the water. And the thing that I love about Mars is, is first of all the CO2. Very abundant in the atmosphere, just like on, Earth greenhouse gases. The other thing is water. You have carbon dioxide and water, you basically can have huge capabilities in terms of production of fuels, nutrients and such. But where's that water?
Because you have the hydrogen.
Yeah, because you have the hydrogen and the carbon in the atmosphere. And so one of the approaches that has gained some really interesting attention is called the Rodriguez well. And this is what they do in Antarctica, where you actually drill down into the ice sheet, you heat up a pool of water, and you can actually pull it out. And so one of the things that NASA and other space agencies have been looking at is, we know that there's ice at the poles. The Phoenix lander literally brushed the surface and had ice there. But as Jeff said, higher the poles, the harder it is to get to. So how far south do those ice sheets go? And if they're within, say, 10 to 20 meters, we might be able to drill down that depth and get to that water. And so this is one of those ideas.
Okay, thank you. Can you tell us a little bit about SWIM project, which is a subsurface water ice mapping project led by Planetary Science Institute and JPL?
So this was very interesting in the fact that they did a number of things. They took the radar data and all the different types of instruments from multiple satellites, ESA, NASA, and others, and tried to understand where's the water on Mars, and particularly subsurface ice sheets. And so over several years of refining their models and using these technologies, they were able to basically map out regions where they have fairly high confidence that water is within what I'll call the near surface, meters to tens of meters. And so really one of the things that we would love to do is verify both from a ground perspective as well as potentially next generation missions that provide better radar than the ones that were flown before.
Thank you. Mars Express has been orbiting the red planet since its arrival in 2003, and the radar named Marsis is developed by a team of Italian and US companies. Could you elaborate on that, please?
Yeah, Mars is operating around Mars since 2003, and it's a sounding radar that allows and to confirm the presence of liquid water. As just mentioned, you can see in a science journal paper that's an Italian team at the confirmation, the first confirmation of the presence of liquid water below the south polar cap. It's still there despite the very low temperature because it's probably very salty, and the pressure of the cap is maintaining it as liquid. Unfortunately, you cannot drill as Jerry was hoping, because it seems like to be at least 1 kilometer below. But it's a very important, and it's one step in the direction of the big. There's a big question about where the water of Mars is now, because in the past it was flowing on the surface. And having this kind of evidence is it's really critical. And recently in January there was discovery of probably presence of ice at a very lower latitude, which is encouraging in this direction.
I understand that. Thank you. Well, with a focus on Moon to Mars, it's often said that the Moon is a test bed for Mars exploration. And let me ask you, Jeff, what characteristics are unique to Mars in comparison with lunar environment?
Well, in many respects, the moon is very different. First of all, it's a lot easier to get there, so the whole economics of getting to the moon, you can get there frequently. And as I said, we have to determine, is it cheaper to take things to the moon or to make them there? Second of all, the chemistry of the moon is very different from the chemistry of Mars, so ISRU processes on the moon are not necessarily applicable on Mars, but I think the real value when we talk about learning ultimately to go to Mars by working on the moon is really operational. It's to learn how to have continuous habitation, vehicles roving, maintaining complex systems over a long period of time. So I really look at from the moon to Mars, it's really operational knowledge that we're going to gain on the moon rather than the specifics of the chemical ISRU processes that we're going to use.
I see it. In a larger context, it's vital to perform demonstrations, technology demonstrations, step by step. But the problem seems to lie in the fact that flight opportunities are quite limited for Mars missions in contrast to lunar missions as of today. What do you think is the best way to keep the momentum of Mars ISRU from now on?
Well, the reason I think that NASA has shifted a lot of emphasis to the moon is because we're going to go there. So the best way to get people interested again in other ISRU processes in Mars is to go there. If SpaceX can really get us there in the next, who knows how many years, but once people are really serious about going to Mars, there will be a revival of the interest in developing the ISRU processes that will keep people alive and help them to work and on Mars and ultimately get back.
I will mention one thing, in the fact that I will slightly disagree with Jeff in terms of that the chemistries are different, and I'll point to the carbothermal reduction, for example.
Fair enough.
Where, yes, the minerals on the moon are different than obviously the minerals on Mars or whatever. But the fact that for carbothermal reduction, we are basically making CO2, we're then converting that to methane, we're then electrolyzing the water that's produced. So there are several technologies and capabilities that we can, if we're strategic in our thinking, select for lunar applications that also are worthwhile for Mars. So that's another way that we could keep the Mars ISRU going.
Yeah, fair enough.
Okay, let's talk about sustainability. And I hope this illustration nicely summarizes the 3 pillars of sustainability for future space exploration, which are environment, society, and economy. And in terms of environmental preservation, humankind has to responsibly explore the solar system, avoiding unintended consequences. In that context, Jelly, have you ever assessed the potential impacts on the natural environment on space frontiers by ISL activities?
So we are starting to do that to some extent. As I mentioned at the beginning, responsible space activities, responsible ISRU are things that we're spending a lot more time trying to understand. So while we're not going to impose any particular requirements or specifications, we're going to try to basically understand that everything that we do now in ground facilities and analog tests, we need to understand the environmental impacts that that could cause. What are we venting? What amount of dust are we generating? And then use that knowledge to go forward and see, is there a better way of doing it? Can we mitigate this? What are the overall impacts? So it is something that, in the past it was just, can I do it? Now it's not just can I do it, but how do I do it is taking a much stronger role.
And also, Jerry, if I can add, it also deals with the idea of allowing that it can be doable also in the future. Because you use some kind of resource, you have to, and an environment, you have to maintain the conditions that can be used over a long time perspective.
Yeah, we, as they mentioned, we as a humankind must always have to keep in mind that a drop in the bucket matters, I think. Okay, the second pillar is society, and it's essential to seek a way to expand space frontiers for the sake of all countries involved. As a great example, Global Exploration Roadmap 2024 was recently published by ISRU, and Simone played a leading role in revising that document. What was the biggest challenge for you to lead the international effort to draw a blueprint for space exploration?
Well, yeah, the GR has been recently issued in September. It was a very interesting effort, and I invite you. There will be a presentation about it on Thursday lunchtime at ESA stand. And yeah, ISRU includes 27 agencies, so you can imagine we have to deal with the 27 different visions from all around the world. So it's quite challenging. But what's interesting there is that it's non-binding forum. So we are kind of more free environment to discuss, without that constraint. It's when for the diplomacy you have informal meetings, you can easily discuss and share ideas without being constrained. So in this kind of environment, we found this as a point of strength instead of a weakness. So I think it was challenging but successful.
Okay, I will skip this slide due to time limitation. Well, the final pillar is economy, which leads us to the next big discussion topic. Well, the space economy is growing at a very rapid rate. According to Space Foundation, the global space economy reached at the $570 billion in 2023, which is 7.4% higher than the previous year. And most importantly, commercial revenues accounted for 78% in total. Jelly, given those numbers, do you feel any changes in the dynamics of the space economy in your country?
Well, I see it globally, but especially in the United States. I've had the benefit of working for NASA for 39 years now. And starting it was very much NASA is in charge of everything. Even with respect to companies or international partners. And as time went on, we became part of the International Space Station and agreements. But again, to a certain extent, it was Russia and the United States leading it. And oh, by the way, we'll have a Japanese module, we'll have a European module. But again, the emphasis was kind of strongly on the NASA side. Government is in charge. But over time, we've now seen a big change and the idea of bringing commercial partners on. It started to some extent with a Sabatier reactor on the space station that many people don't realize. But then we got into cargo delivery and crew delivery. Now we have spacesuits and HLS, human landers. We have the CLIPS program. And so you're seeing much more public-private partnerships, and I see that transitioning into now having pure commercial missions, Axiom and such. So it's been a tremendous change over time, and I'm excited by that level of interaction and again, joking at the beginning, what can the government do to enable these things to go forward is now, the charter of STMD and much of NASA versus, we're in charge.
Mm-hmm. Yeah, thank you. Well, Catherine, I suppose the ultimate goal of the startup support program is not helping startup companies making IPOs and M&As. I think that is for building a thriving ecosystem for ISRU activities. In that context, what is the biggest challenge for you as a director of ESRIC at this moment? And what do you envision for the future?
I think one of the biggest challenges, not just for me, but for the entire sector, is trying to establish how we do this. There is currently nothing, apart from MOXIE. MOXIE aside, there is no very limited space resources activities. And what we're trying to do with our incubation program is to identify and select companies that can survive and thrive in this hugely uncertain field. So we're trying to do everything at the same time. We're looking at construction, at power, at extraction of oxygen, water, and manufacturing, repair. All of these aspects, developing technologies, concepts, architectures, all at the same time. And that lends a huge amount of uncertainty in how we move forward. So one of the things that we're trying to do with our incubation program is identify innovative concepts in companies that can survive the uncertainty in the near term and that can really support this future vision in the long term.
I see. Thank you, Catherine. It should be noted that where is the clicker? That's funny. Oh yeah. Whatever. Oh wait, there you go. Okay, well, it should be noted that academia has played a vital role in the aerospace arena over the past century. Jeff, do you think, what is the responsibility of academia through the lens of open innovation to expedite project cycles, which ultimately leads to the cost reduction?
Well, the thing about academic research is that you have a freedom to explore new ideas, to try out new processes, new chemistry, physics, without having to worry about, is it going to make an immediate profit? That's what universities have always done. The academic research, you are sort of free to speculate, to have new ideas, and some of them work and some of them don't, but even the ones that don't, it's okay, because that's what the universities are there for, is to try out new things. And now ultimately, the things that are successful, then you make a small company and it becomes a commercial activity. But you have the freedom to start that out, and sometimes they work and sometimes they don't.
Thanks for your insight. Thank you. Well, for those who are seeking opportunities to get connected with ISRU community, conferences are good starters. And we would like to introduce two international discussion platforms. One is Space Resource Week, as Catherine mentioned in her presentation. When is the next conference and how do we sign up for it?
The next conference in sunny Luxembourg will be on the 19th to the 21st of May. We will be launching a call for abstracts shortly in the next month or two. So keep watching, keep following our LinkedIn page and our website for more information.
Okay, just to make a quick clarification, is it a hybrid conference?
It is hybrid. It is both in person and online, but we do request all speakers are there in person.
Okay. Another conference is Space Resources Roundtable. For the audience, please raise your big hands if you have ever participated in Space Resources Roundtable. Great. Please ask them how intensely wide-ranging topics are packed into week-long session. And the next Space Resources Roundtable, which is the 25th anniversary, is scheduled at the beginning of June next year in the United States. For the details, please scan the QR code or you can just Google it. Now, we have some time for questions from the audience. Please post your questions on Slido app. Well, if you have any questions to other speakers, please go ahead.
Well, June, you haven't had a chance to actually talk about JAXA and what's happening in Japan. So I think the audience would be very interested. We're all excited about LUPEX, for example, because as most people know, Viper may not be able to fly. So LUPEX would be one of the first missions that could actually go into a permanently shadowed crater, and you have other ambitions, so please tell us about it.
Yeah, from my perspective, our focus is on propellant production. So after getting ground truth data by LUPEX, we're gonna consider that data to the design of our ISRU plant. And we already have performed a conceptual study of ISRU plant for propellant production, but we haven't reached a conclusion yet. So we need to update the numbers using those ground truth data.
What do you think about operating in the permanently shadowed regions at 40 degrees Kelvin? I mean, we don't have a lot of machinery at this point that can work at those temperatures.
Yeah, you hit the nail on the head, and we need to perform environmental resistance testing on the ground a lot, so we'll see.
I was very impressed. I did get to hear the Dan Andrews Viper presentation earlier this morning about going into Chamber A, which is the largest vacuum chamber at Johnson Space Center, getting down to 15 Kelvin and being able to operate. And in fact, they were saying they didn't get cold enough for some of the instrument heaters to turn on.
Okay, here's a lot of questions, and the number one is, how long do you think it will take for first lunar ISRU technology to reach level 9 readiness, technical readiness level, TRS 9?
Okay. Well, I can. So TRL lunar, yeah. So TRL 9 refers to basically operating on the lunar surface versus into a vacuum chamber, which might be TRL 6 or 7. It's a good question. We, with respect to Lift 1, which was a request for information that the Space Technology Mission Director had put out, looking at the first oxygen extraction demo, we're now through a process of budgetary aspects and reorganization that we're not quite sure where that will go. That said, I am very excited by many of the commercial companies out there that are looking at performing demonstrations. ESA has several activities going on with respect to lunar ISRU. So I have no idea when the next one will be, but and to some extent, maybe even Prospect could be considered an ISRU demo if they are successful in extracting water.
Okay, we now almost reached the end of our time, and my last question to the speakers is, what's next for you? Simone, you can go ahead.
Well, I can just reinforce the same message. I think now we start to consider dedicated initiatives to SRU and from the perspective to the demonstration, but then move forward, because TRL with the demo mission in a small scale is not enough. Now we then start thinking how to move from demo of the technology and capability to the large plant that are expected to be there. So this is probably the next one. And I also hope that dealing with the ISRU will also force us to learn how to deal with the scarcity of resources. That is something that we have to face also on the Earth. So teach us that we have to consider these things also for our future here.
Thank you. Catherine.
Briefly, growth. So ESRIC's 4 years old. We're about 25 people. We are looking to grow all of our activities. But also, we're pretty uniquely placed in the world of ISRU as being a centre of expertise entirely dedicated to it. So we're looking forward to supporting the sector in towards implementation.
Jeff Lee, please.
Well, I'm an operations guy, so as far as I'm concerned, the next step is let's get some people to the moon. I mean, get them there living for a long time, and then we'll have to get serious about ISRU. And let's do it to Mars as well, because until we actually get people there and are living, it's just going to be theoretical.
Why not? Yeah, you can go ahead.
So from my perspective, it's two parts. One is obviously keep moving the ISRU space ball forward as much as possible over the next several years. But I'm really also excited about what Simone had mentioned, and that is how does ISRU relate to challenges on Earth, and how can we solve those things? So we are talking to the mining industry quite a bit. You know, the fact that CO2 processing and water processing might support alternative fuels and greenhouse gas challenges and such. That really is exciting because we're not going to make money on the moon or Mars anytime soon, but the companies that are planning on doing that, if they can help challenges on Earth and actually make a business case around it, then that's where we're going to go.
Thanks, everybody. Well, as a closing message, there are a lot of challenges to overcome in order to commercialize space resource utilization, but I firmly believe this really is a fun field with great opportunities and wonderful puzzles to solve. So please stay tuned on the latest developments of space resource utilization and enjoy the rest of your stay in this beautiful city. Thank you. I appreciate that.